Okay, so the question that we're considering today is how does the center of mass velocity of a rolling object, this velocity right here, compared to the tangential velocity of a point on the surface of the rolling object, this velocity right here. And what I'm ultimately going to try to show you is that those two velocities are actually equal to each other as long as there's no slipping between the wheel and the road. Which to me is just bizarre. I remember when I first learned that, I was like, what? But if this is a wheel that's on a car, and the car is going down the road this way, 50 miles per hour, well, then if you take a look at a point on the tire at its tangential velocity relative to the center of the tire, guess how fast it's going tangentially relative to the center? The same, 50 miles per hour. So let's try to prove this to ourselves. So here we have this blue wheel here, and let's say it rolls forward a distance exactly equal to its circumference. So basically, if I took that tire, and I cut open the tire, and then I rolled the length of the circumference out linearly. If I roll the length of that out linearly, from here to here, that from there to there would be the circumference. So of course, from here all the way around to there is the circumference. And from here all the way out to here is the circumference. Well, if this tire up here rolls forward a distance that's exactly equal to the circumference, we could say that this distance from here to here is exactly 1s, one time all the way around. S for the arc length all the way around the circumference. So we know that the tire its linear velocity forward, we know that velocity is equal to the change in the forward displacement over the time. And in this case, how far forward did it go? Well, it went forward a distance s in a certain amount of time t. But meanwhile, this particular point on the outside, it started here, but when that tire rolled forward one circumference, what did it end up doing? It ended up going all the way around, and when the tire has gone halfway, where would that particular point be? At the top right there. And then after the tire has moved forward a whole circumference, where would that point right there be? Back at the bottom. So how far around the outside did that particular point right there move? Well, it moved relative to the center. I'm not talking relative to the road because that's a whole nother ball game. I'm talking relative to the center. Just looking at the rotating tire and neglecting the fact that it's moving down the road. Well, the rotational velocity change in the arc length S over the time. And basically, it went the same distance all the way around, the same distance in the same amount of time. So it too went a distance S in the same amount of time. So the center of the object went from here to there, a distance S in amount of time t, and the outside, a point on the outside, went all the way around from here to there, a distance S in the same amount of time t. So how does the velocity of the center of mass right here compare to the tangential velocity of a point on the outside? They're absolutely equal. Which is just, to me, it's just, what? So the answer to today's question is so you have this wheel that has a radius of 0.50 meters. It starts with initial velocity of 0 and it rolls down this ramp. The acceleration of the center of mass is 2 meters per second squared. That's how fast the tire is speeding up as it rolls down that ramp. And the wheel rolls to the bottom of the ramp in 4 seconds. The question is, how many times did that wheel go around as it went down the ramp? Well, we could calculate this distance down the ramp from here to here. We could calculate this distance, call it S. Just using the great displacement formula, old school, we know that x is equal to VIT plus 1/2 AT squared. So in this case, we're calling that distance x, S, down the ramp. And the initial velocity of the wheel going down the ramp is 0. So it's 1/2 the acceleration, which is 2 meters per second squared, times the time squared, which is 4 seconds squared. So that distance down the ramp is going to be 16 meters. Now, if there's no slipping, which we can assume since they didn't mention anything about slipping, if there's no slipping, then just like we could say that the tangential velocity of a point on the surface is equal to the velocity of the center of mass, we can also say that the arc length S that a point on the outside went around is equal to the distance that the center of mass went down the ramp. In other words, if the wheel rolled down the ramp 16 meters, we know that if we put a point right here, and we measured the distance that it went relative to the center. Never mind the fact that the ball is going down the ramp, completely forgetting about that point, but just measuring the distance. Well, this particular point right here, how far around was that circumferential type distance as it went down? Well, it too would be 16 meters. So the distance here, this is the distance that a point on the surface of the wheel went around their circumference. Is equal to the distance that the center of mass moved forward. So now we just look at that wheel, and if the radius r is 0.50 meters, what's the circumference, the distance all the way around? The distance all the way around once would be circumference equals 2 pi r, and in this case it would be equal to 2 pi times 0.5 meters, which would be equal to 3.14 meters, pi meters. But we know that when that wheel rolls down the ramp, the center of the wheel rolls forward 16 meters. So a point on the outside of the wheel is going to roll around the circumference 16 meters. So how do we figure out how many times?
16 divided by 3.14.
Right. So then we say, look, 16 meters divided by 3.14 meters. And what does that turn out to be?
Because there's
5.1?
yeah, round. Because there's no slipping, the speed of the object does not matter in terms of how many times it'll rotate.
Well, yeah, it does matter.
Well,
Distance it covers.
You know, we covered that by figuring out this distance here.
Is the distance it covers.
oh, okay.
So 5.1 revolutions, and that's your answer.
So that's the answer.
That's the answer.
It's not that difficult. Yet.
It's just a concept.
Yeah.
Right. All right, let's do another problem. So the essence of this lesson is that when you have a rolling object and there's no slipping, the speed of the wheel itself moving forward, which I'm calling the velocity of the center of mass, is exactly equal to the speed of a point on the surface relative to the center, the tangential velocity. And that's what you basically need to know. Those two are equal to each other to solve the problems. This next point, I'm not even sure if it's going to come up in any problems or anything. And I'm almost hesitant to share it with you, but yet it's so gosh darn cool that I just want to show you this. But I don't think you're necessarily going to use this when solving problems. When solving problems, you're just going to compare this tangential speed of a point here and that center of mass, and those two are equal. So this here is equal to that right there, center of mass. But the thing is, this is the tangential velocity of a point on the surface relative to the center. And of course, this is the velocity of the wheel going down the road. This is what you need to know. This is what you're going to have to use in problems. Here's the last little side point here. Ready? What if, though, we wanted to consider the velocity of a point on the surface of the tire, not relative to the center, but relative to the road? And I'm not even going to prove this to you. I actually have to think about it myself, like how would I actually prove this? But I know this to be true, and this is just kind of fascinating. Watch. As this tire goes around, yes? Like this, yes? Well, look. When it gets to that top point right here, it's moving forward relative to the center because of that roundabout motion, yes? Plus, the whole son of a gun tire is moving forward. When that same point comes all the way down at the bottom right here, relative to the center, which way is it going? To the left. It's going this way. Relative to the center. But yet, which way is the overall tire going? To the right. And how do we know that that tangential velocity to the center, how does that tangential velocity to the center compare to the center of mass going to the right? They're the same. So, if you were asked, hey, what's the overall velocity of that point right there when it makes contact with the road? Somebody said it. Zero. At the bottom right here, at that bottom point right here, its tangential velocity is the same as the center of mass, but you got to remember the whole tire is going to the right, but this little point is going to the left, so its total velocity, the total velocity right here of a point on the bottom is equal to zero. But what about when that same point comes around and it's up top of the wheel? Then not only is it going forward with a tangential velocity relative to the velocity of the center of mass, but then the whole tire is going forward as well. Anyone want to take a guess what that velocity is equal to when it's at the top point? Relative to the road, not to the center.
Is it 2 times the velocity?
2
the velocity of the center of mass.
So at this point right here, how fast is this point going relative to the road? 2 times the center of mass velocity. Like I said, we don't use this in any problems. In problems, we're using this fact right here. But come on, that's kind of interesting. The top point of the tire, its speed relative to the road is twice as fast as the car when it's at the top, and it's 0 relative to the road at the bottom. Think about it. It has to be 0 relative to the road at the bottom. Otherwise, what would be happening? It would be sliding. The fact that it's not sliding means it's not moving relative to the road. It's so bizarre. Right there, the velocity of the tire relative to the road is 0. Up here, it's going twice as fast as the speed of the car. Take a break. We'll reconvene in the next room.